Okay, so 7.4, number 2. So it says the graph at the right gives spring force, Fs, versus position x for the spring block arrangement that we've been using, right? So your graph basically looks like this. You've got horizontal position measured in centimeters. You've got spring force, and then the graph looks like this. You're told that this is 2 centimeters, and this force up here is 160 newtons. Down here, you're going to have the same thing, right? You're going to have positive 2 centimeters and negative 160 newtons. Cool? Does everybody understand what the graph is telling us? Okay, so it says we release the block at x equals 12 centimeters. So the problem here is that 12 centimeters doesn't show up anywhere on the graph, does it? Okay? So what were you intended to use this graph to do? Okay, find the slope. Why would finding the slope help, Nana?
Because that's k, right?
Because that's k, right? Okay? Or, I didn't even think of it as, I mean, what you're saying is 100% true. The slope is your k.
I actually just used the equation.
But yeah, I mean, basically what it is this. Look, it's linear. So we know that the force of the spring is negative kx, right? So, pick a point and solve for k. So, I don't know, let's pick this point. So at that point, the force of the spring is negative 160 newtons. That's equal to negative k times x, which is 0.02 meters, right? 2 centimeters? Yeah?
I'm confused because I thought that each unit was 160.
Oh, am I wrong?
I don't know.
Nope. Yeah, so if you look at it, there's a little fs up at the top of the graph up there.
Oh, okay.
And it says fs equals 160.
All right.
So that may have been what messed you up. Does that make sense, you guys?
Yes.
Okay. So solve this. Divide both sides by 0.02, and your k ends up being, what does that give you, 8,000 or 80,000?
8,000.
8,000, thank you. 8,000 newtons per meter. Okay? All right. So it says we release the block at x equals 12 centimeters. How much work does the spring do on the block when the block moves from 8 centimeters to whatever? All right. So the fact that you're releasing it at 12 centimeters really isn't important. All that's saying is you stretch it all the way back to 12 centimeters, and then you let it go. So it's going to go, it's going to oscillate back and forth, and it's going to make that funny noise as it does it. Okay? So, exactly. So does everybody understand that it's just going to go back and forth? Right. Okay? So, to find the work done, it says how much work does the spring do on the block? So we're trying to find the work done by the spring, right? So, the work done by the spring is just the change in elastic potential energy with a negative sign stuck in front, right? So, all you got to do is find the elastic potential energy at 8 centimeters. So, my initial elastic potential energy is going to be 1/2 k. Whoever's whistling, please stop. Thank you. Times x, which is 0.08 meters squared. Good. All right, so that gives you 0.5 times 8,000 times 0.08. Don't forget to square it. Everybody good with that? All right, so now in part A, we want to figure out how much work is done between here and 0.05 meters. So find your final elastic potential energy. So that gives you 10 joules. All right, so, oh, sorry, that's okay. So look, between here and here, we lost, so our change in elastic potential energy here is going to be negative, what, 15.6? that make sense, you guys? And so the work is going to be positive 15.6 joules. Peter, in the deck?
So I just tried to like find the area under the curve. Why wouldn't that have worked?
If you find, well, okay, so A, that does work. B, you need to extrapolate your data, right? Because your data doesn't go this far.
Yeah, so I just like,
So did you just like embiggen your graph?
oh wait, actually I know exactly what I did now. Because I made the mistake of doing the, like each one unit was 160 newtons when it should have been 80.
Each one is 80.
And that's why I got a double.
So you got double the answer. Yeah, that
And
makes
I was
perfect
so
sense.
confused as to how that happened, but I just realized.
Gotcha. Okay, so yes, that will totally work.
Okay, cool.
Yep. Dan, sorry.
Yeah, no, it's okay. So the integral formula that you gave us is like the same thing as what you just did, right?
Correct.
Okay. Yeah.
Oh, right. Oh, that's another way you could have done this. Totally. Yeah, you could, so, yeah. So look, here's this. So the other way you could have done it is you could have integrated the force of the spring with respect to x between the two given positions, right? You're going from a position of 0.08 to a position of 0.05. And that accomplishes the exact same goal. Very good. Very good. Are we good with that, you guys?
Yeah.
All right. Just so you know, you guys, I'm still, because this is just my second time through, I am stealing problems from the book. And that notation that they used here where it says Fs is set at blah, 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 that's common. Okay? So when you see that, that's what it's telling you, you know, what the value at that one point is, not the value of each block. Okay? That will, I'm sure, come up again. Okay? All right, any problems on 1 or 2? Okay, how do we do with 3? Good with 3? Anybody want me to discussify it? Okay. I know I need to talk about, okay, so I don't know, I'm jumping in. How about 4?
4.
That's fine.
I'd like to do 3. I didn't get 4, but I didn't like that. What?